All right, so today we're going to go over Doppler effect. Which one of my key points on the screen there is wrong? Nope, that one's right actually. That one's true.
Well, you only have it's the other one, because that's the only other one that could be.
Well, no, it could be learn what the Doppler effect is. That could be wrong. Okay. No, it says here, understand how Doppler effect changes the pitch of a sound. What property of waves goes with pitch?
Frequency.
Didn't we just say like 100 times that frequency can't change? Okay. So why would I write that as a key point? It seems contradictory.
Because it's a perceived pitch, the frequency doesn't actually change, but the sound appears to change pitch.
Right. It's a perceived change. It's not an actual change. The frequency of the waves does not change. But because either the source of the waves or the observer, or both, are in motion, our perception of the frequency of the waves changes. Okay? I'm going to do a little demo here. I'm going to need somebody to be the other half of this demo. Where you take that, I see you got your hand up there. Okay, so I'm going to have you take these hands, put that one in your left, this one in the right. Okay, and let's just have you walk over to that corner. We'll get this stretched out. Okay. All right. Can I have you go like on the other side of the loop there? We're going to get this nice and tight. There we go. We're going to wing it right through everybody. Okay, so put your hands together there. Oh, put them together. There we go. I'm going to get it to slide toward you and then we'll get it started. Okay, everyone hears the sound? Okay. Oh, we got it stuck in the middle. I've never actually done it this way. I used to throw it, and then I thought, that's a lawsuit waiting to happen. There we go. There we go. Beauty. Woo! Oh, the knot's coming undone. That was a good one. Okay, can you guys hear the change in frequency? Otherwise, it's just two guys playing with a toy. There we go. Now we got it going. Okay, that was fun. Oh, they quit. That's not good. Oh, there it is. Beauty. Thank you. I don't know if the microphone picked that up. Okay, so Doppler effect then is this perceived change in frequency. The place where you've probably experienced it the most is an emergency service vehicle. Okay, a police car, a fire truck, or an ambulance. Okay, when they're coming up on you, they sound different than when they're going away from you. Okay, and that's because of the Doppler effect. Okay, now I've got a couple of videos on that. That actually have really good sound. The video is not terribly good, but the sound is. All right. So, fire engine, but an English fire engine, because they have cooler sirens. Okay, as it's going away, the pitch falls, right? It gets lower. Okay, same thing with a car horn. Okay, anything as it goes by, and the effect is amplified the faster you go. Okay? The faster you're going, the greater difference in speed, I should say, between the source and the observer, the greater the Doppler shift. But there's your next costume idea. You can be the Doppler effect. Okay, so what the Doppler effect really is if an object is moving towards you and you're stationary, okay, it's producing waves at whatever frequency, like when we were running the Doppler rocket across, it was producing a certain tone. But as it approached you, it sounded like that tone changed and got higher. And the reason for that is as it made a wave, the wave traveled away from it. But it didn't travel as far away from it as it would if it was stationary. And so then it produced the next wave at the same frequency, but because the wave didn't get a chance to get as far away, the next wave crest to us seemed like it was closer. So we heard a higher frequency or shorter wavelength of the waves because of the motion of the rocket. Okay? As it went away from you, it would produce a wave and then run away from it before it produced the next one. And so it seemed like the frequency got lower because now the waves seemed further apart to us. They're not actually. Okay? It's still producing waves at the same frequency, but because it's moving, our perception of that sound is now altered. Okay? This is where the sound barrier part comes in. Are jets loud? Really loud, especially when they're at full throttle. Okay? They're incredibly loud, like instant perforation of your eardrum. Okay? So if I've got a plane that's approaching the speed of sound, which is where the sound barrier exists, okay? It's approaching the speed of sound. That means the waves it's making, the sound waves, which have a large amplitude because it's loud, are going pretty much the same speed as the aircraft. So how far away from the aircraft do they get? The answer is they don't. They travel right with it, and it's constantly making more. So what happens to all the waves in front of the aircraft? Well, a little bit maybe, but not exactly what I was looking for. They might diffract a little. So let's say normally the plane makes waves that look like this, if the plane was stationary. Okay? If the plane is moving at the same speed as the waves it makes, those four waves look like this. Because they can't get away. They're going the same speed as their source. So in front of the plane, you've got all these waves that have piled up on top of each other. Now, sound waves are a series of compressions and rarefactions. It's compressed air. So what's happening to the air in front of the plane? Yeah. In fact, the air in front of the plane becomes so dense, so pressurized, that water will turn back into a liquid from a vapor because it's under pressure. What is that, Charles' law or Polar's law? Ideal gas law? It's one of those ones. I don't remember my chemistry. Okay? It's one of those where you put pressure on a gas, turns back to a liquid. That's the thing. I just don't remember what it's called. Okay? It's one of those. One of those three. Or maybe they're all the same thing. I don't know. Okay? So anyway, you compress that air in front of the plane. Okay? The air becomes incredibly dense. So dense, in fact, that before they designed planes properly, planes would smash into it and be destroyed. But that's what it looked like from the ground. It wasn't actually what was happening. But from the ground, they saw a plane going faster and faster, and then its acceleration would just drop, and it would get stuck at right around Mach 1, which is the speed of sound, right around 330 meters per second. Okay? And it would start to shimmy and just buffet like crazy. Okay? Because it's like it's trying to fly through super dense air. Okay? To the point where it would just shake the plane apart. The plane would blow up. Okay? From the ground, that looks like a plane running into a wall in the sky and blowing up. Okay? That's what it looked like from the ground. Hence the term sound barrier. Because unfortunately, there weren't any test pilots to ask after. Right? This was a hard time to be a test pilot. although there were, those guys that just, man, I want to be the guy that gets through the sound barrier. They were lining up for the chance to smash into that invisible wall in the sky, okay? But it was a big problem because they didn't understand what was causing the planes to basically disintegrate. Okay? So what they just kept doing was making more and more powerful planes because, it's just that the plane isn't powerful enough. Okay? I mean, that's, at that time, it's a very male-dominated, kind of situation, and there's about more power, and that's like, yeah. So the last plane, the plane that actually finally broke the sound barrier was basically a rocket with little tiny wings on the side. It looked more like a missile than a plane. And it couldn't take off on its own. It was dropped out of a bomber. Okay, so they put it inside the bomb bay of like a B-52, or not a B-52, the B-28, whatever the big prop one was. Okay, and they're flying this thing up into the high altitude because they know, it's easier to, it should be easier to break the sound barrier, sounds slower, high altitude, so they take it up there and they drop it out of the plane. And the pilot flicks the switch that lights the rocket engine. And it's like, all right, I'm either going to be on the ground or on the ground in pieces. Okay, you're committed. Flip the switch. Okay, so the person who first broke the sound barrier, his name was Chuck Yeager. Okay, he actually had broken ribs when he actually broke the sound barrier. He had fallen off a horse the night before, and he knew that if he told anybody that they would not let him pilot the aircraft, so he hid it from everyone. He asked the main hangar guy for a stick so he could close the hatch on the plane because he couldn't reach up because of his broken ribs with his hand. He could pull the hatch shut, so he had to get a stick from the guy. So anyway, he hit it and he was able to fly the plane. And what he found, they had changed one other thing on this plane. Okay? Most of the planes had a pointed nose because they want to be aerodynamic. Glamorous Glennis, which was the name of the plane that broke the sound barrier, had the pointed nose and like a spear-looking thing coming out the front. Okay? Now, the idea here was that the spear would create a better aerodynamic situation and disrupt the air in front of the aircraft. So he starts flying this thing, he starts getting near the speed of sound, and the plane starts to shake, just like every plane before it. The plane starts to shake violently, okay? But all of a sudden, he looks at the speedometer, and it's jumped, okay? And he is going faster than any person has ever gone, by nearly a factor of 2, okay? And it happened pretty quickly, not instantaneously, obviously, but once he got through the sound barrier, all his sound waves fell behind him. And suddenly, he's got a super powerful, super aerodynamic aircraft with very minimal drag in front of it, because all that air has fallen behind him. Meanwhile, on the ground, people are watching this, and they see a puff, the compressed air, the water vapor condensing back into a liquid, and they hear a massive bang. And they're like, no, back to the drawing board. Chuck's dead, and we gotta we gotta build another plane. We're screwed up again, like what are we doing wrong? And then over the radio comes Chuck Yeager. I think there's something wrong with my Mach meter. It's jumped plumb off the scale, because he's a test pilot. He's like, if I can go fast, I'm gonna go fast. I'm gonna go as fast. He had pegged it. And, I mean, the thing went to like Mach 1. And then there was a little bit in case you actually got through the sound barrier. And he pegged it. He was going way faster than that, nearly Mach 2. Okay? Because, he was flying a rocket. And once he had gotten through the sound barrier, there was nothing to stop him. And they're like, hey, Chuck, can you land that thing? Because, kind of important that we figure out what we did right here. Okay, you're alive, that's great. Don't wreck the plane. Okay, you need that thing on the ground. And that's what they figured out, is that you have to create some kind of disruption in this wall of compressed air that forms in front of any aircraft that is going near the speed of sound. Okay? Once you get through that, it's actually quite a bit easier to accelerate, because that wall of very dense air is now gone.
So Mach 1 is the speed of sound.
Yes.
Mach 2 is
Twice
two
the speed of
times.
sound, yes. The Mach scale is multiples of the speed of sound. So there aren't a lot of aircraft that go faster than Mach 3. Right? Like it's, when you get to those kind of speeds, the air resistance is not so much that it's stopping the plane so much, it's more that it's heating the plane up a lot. Okay? Like the SR-71 Blackbird, that old spy plane from like the 80s, when they would land that, the pilots would have to stay in it until they could cool the skin of the plane. It would be that hot. It's like, you know, why a spacecraft can burn up if it doesn't re-enter the atmosphere properly. Same thing, it's just the speed they're going and the ablative effect of the air. Right? So it's a big deal to go much faster than that. Plus, it consumes fuel like crazy. Right? To be going those speeds, you have to have the jets at full throttle, the afterburners on, and that consumes huge amounts of fuel. So your range is, you know, significantly decreased at those speeds. But we can make planes that go that fast, although most modern aircraft actually now don't go as fast as planes from back in the 70s and 80s. Right? They're more maneuverable and have less of a radar cross-section and all that kind of stuff. Before it was all about, if we can go faster, we can outrun bullets. And they were right. Like the SR-71, you couldn't shoot it down with a machine gun unless it had slowed down. At its top speed, bullets wouldn't catch it, just faster. And it's crazy. But missiles could, because missiles can go much faster. Okay, everyone all right with that idea? Okay, so Doppler effect then looks like this. Okay, if the plane is, you know, going at a low speed, then yes, the waves in front are piling up a little bit, the waves behind are spreading out a little bit, okay? But when you get near the speed of sound, they pile up in front, and they spread out a lot in the back. So a plane traveling close to the speed of sound, as it approaches you, what is it going to sound like?
Giant wall of sound.
Frequency. You're right, it's going to be very loud. If you hear it at all, it'll be a squeal, an incredibly high-pitched sound, because all those waves are piled up like this. When they cross you, it's like a whole bunch of wave crests really, really quickly. Okay, so a very high frequency of sound. Now, the other part of that is if once you break the sound barrier and you punch through that, there's a release of the pressure. That's the sonic boom. Okay? It's the release of all that pressure that was in front of the plane, building up in front of the plane. That's the boom. Okay, and if you're close to that, it's super loud. Okay, planes don't typically fly close to the ground for safety reasons, so it's not that it's going to be, you know, going to hurt anybody, but it's, you know, it's something to be concerned about for sure. When they first learned how to do this, the next thing was, can we use that as a weapon? Right? Can we like have a plane fly nice and low over the ground, break the sound barrier over top of some troops, and like have this shock wave, like throw them out of the trenches and whatever. And it was discovered that you'd have to be basically right on the ground for that to work. And there's kind of a problem with that. They can shoot at you. Okay? The sneaky part would be that they're not going to really hear you coming, because your waves and your plane are traveling together. So they don't really hear you until you're there. Okay? Now they see you, you're cooked. They're going to see you on radar, okay? But you might be below the radar if you're really, really low to the ground. But what they found is the effect dissipates really, really rapidly, like anything, like any force. Okay? It dissipates rapidly through a three-dimensional space. So it wasn't terribly effective, especially since it put them within range of small arms fire. Anybody with an RPG can shoot them down pretty easily. So, this is what it looks like when a plane breaks the sound barrier. This is that cloud I was telling you about, that all that water vapor is under so much pressure, okay, that it turns back into a liquid. And then once the pressure is released, once the sound barrier is broken, it just goes right back and it's gone. Okay? It's a cloud that forms for an instant and then it's gone. Okay? And there's actually two that form, one at the nose and one at the tail, because you got those additional tail fins that are up, and they kind of have additional drag effects that produce a second. You can see kind of one here and then one near the back of the plane. All right, I'll show you a couple of videos here. All right, so if we have a stationary train, okay, this is what the sound waves look like. Person in front, person behind, hear the same frequency of sound. okay? Because the waves are all traveling at the same speed, they all have the same wavelength, all the same frequency, okay? And they're traveling outwards. Once we get the train in motion, okay, in front of the train, the waves are going to bunch up, okay? And so the wavelength that we perceive as the train approaches is different than the person who's behind the train and the train is leaving, because those waves are getting spread out, okay? The train's whistle is the same frequency. That hasn't changed. You have to change the whistle in order to change the frequency. But our perception of the waves is different because of the motion of the train. And the same would be true if I was in motion. Okay? So if there's a stationary sound source and I'm moving towards it quickly, I hear it differently than a person who's standing still that I run past. Okay? Now, running, you got to run pretty fast, okay, for that to be noticeable. But if you were in a car or something like that, okay, you'd definitely be able to perceive that the frequency of the sound is different when you're in motion versus when you're stationary. So it's either one. Either the source is moving, or the observer is moving, or both. Okay? If I've got a source that's moving towards me and I'm moving towards it, is the effect going to be even more amplified? Definitely. Okay? And that is absolutely the case. Okay? The formula for Doppler effect, we don't actually use the full formula in Physics 20. Okay? But it's the Doppler frequency, okay, equals the original frequency multiplied by V plus or minus VO over V plus or minus VS. Okay? So VO is the speed of the observer. VS is the speed of the source. And there's a plus or a minus in there. How do we decide whether to add or subtract? Right, if it's moving closer or if it's moving away, okay? So if I've got, let's say, so I've got my frequency of sound here, my original frequency. If the source is moving towards me, I'm going to hear a louder frequency of sound. Okay, so let's just imagine that I'm not moving. Okay, I'm stationary. So I just have the speed of the waves. Okay, this V stands for the speed of the waves, speed of sound. Speed of the waves divided by the speed of the waves plus or minus the speed of the source. Would I want to add or subtract for an object that is approaching me?
There's a question
Oh,
about
okay.
what we have on the formula sheet.
Yours is different on the formula sheet.
Yes.
We don't do moving observer problems, but I still talk about moving observers for the sake of kind of illustration. Okay, so if the source is approaching me, will I add or subtract? Okay, the gut is add. The gut instinct is add. But think about it logically. This number, if the source is approaching me, is bigger than this number. And that's where the gut part of add comes in. But think about this part. I'm taking this number and dividing by this number. If I want F1 to be bigger than F0, I need what's in brackets to be greater than 1, which means I need the top to be bigger than the bottom. Do I add or subtract? Subtract. Okay? Now, what if I have a moving observer? I would add. Yeah, so I got a source that's moving towards me, I got an observer that's moving towards, or I've got a source moving towards the observer, I got an observer moving towards the source as well. Add the speed of the observer, number on top gets even bigger, subtract the speed of the source, this number gets even bigger. Okay, and then I multiply it by F0 and I get a bigger Doppler shifted frequency. Okay, everybody all right with that? So for you guys, for whatever reason, a couple of years ago, they took out moving observers. I don't know why, it doesn't make the questions any harder or any easier, but they took it out. Okay, so you only have to worry about moving sources. So you just basically have to memorize. If the source is moving towards me, I subtract. If the source is retreating or moving away from me, I add. Okay, because that'll make either a bigger number in the brackets to multiply by and make F1 bigger, or it'll make a decimal, which when I multiply by F0 will make F1 smaller. Okay? All right, so we see this effect. We can experience this effect with sound. Okay? Because sound is a fairly slow wave, we're capable of moving fairly fast and even faster than sound itself. Okay? So we can perceive this Doppler shift. All waves do this. Light too.
I was just going to ask, is there such thing as a light barrier?
Don't know. I would guess there's some sort of effect there, but we certainly wouldn't be breaking the light barrier within the Earth's atmosphere where there's a medium, right? In the vacuum of space is likely where we would do it, so there's no medium to bunch up in front of the spacecraft, right? Now, that said, there's all these ideas about, warping space and traveling on a wave that goes faster than the speed of light. Those are ways to travel, to have faster than light travel is to create this wave in subspace that you can ride, okay? Kind of like surfing, you're kind of like surfing this bubble, okay? Or disruption of the wave that can go faster. But who knows? It's all so theoretical at that point, right? In all likelihood, there wouldn't necessarily be a light barrier, but it's also energy prohibitive to go that fast, right? That's that whole E equals mc squared thing. Basically, is a layman's way or a simplified way of showing that the energy required to approach the speed of light becomes infinite. Yeah, something like that. Like it's crazy. Okay, but there is a Doppler shift for all waves, including light waves. Okay, now we don't move fast enough on Earth to notice a blue shift or a red shift in light. Like, it's not enough for us to notice it or detect it with our eyes. But we do have instruments that are capable of detecting those tiny little shifts in the frequency of light. Okay, it's why we know the universe is expanding. Okay, when we observe objects in the universe, okay, especially very distant objects, we notice that their light is Doppler shifted slightly red. Okay? If it's Doppler shifted slightly red, that object is moving away. Okay, so things far away. I mean, obviously, if you look at a planet, there's times where it's moving towards us and moving away from us. We can't really use that as to say, hey, the universe is expanding. Okay? Within our little area of the universe, it doesn't really work. Okay? If the planet's moving away, sure, it's going to be red shifted. When it's moving towards, it's going to be blue shifted, but it's not something we can really detect. Okay, but more about like very distant objects, kind of surrounding lights. Okay, that's in the universe we can see is shifted slightly redder than it should be.
Is that how they figured out the Andromeda galaxy is coming towards the Milky Way?
Yes. Yeah, it's that kind of stuff that can help us figure that out. Doppler effect, Doppler shift can help us detect not only that it is moving that way, but how quickly. Right? If we know the light from this galaxy should be approximately this wavelength, or this frequency, but we're detecting this, we can use that formula to figure out how fast the source is moving. Now, that would probably require us to consider ourselves stationary, or we would have to know how fast we're moving as well. But yeah, it tells us all of that stuff. Okay, is that making sense? Okay, that formula. Manipulation. A little weird? Not too bad, okay? People used to get really intimidated when it had the plus or minus VO in it. You gotta remember when I'm adding or subtracting, you gotta move everything around. It really wasn't as bad as people made it out to be. Okay? You just have to make sure you kind of do it in order. And we'll look at the manipulations here in a little bit. Okay, so we got the bunching up in front, we got the spreading out behind, okay, simply Doppler shift. We talk about sound all the time just because that's the one that we notice, the Doppler shift. But you would also notice it if you were traveling in the water. Okay, so if you've got waves coming into the shore and you're going out into the waves, okay, do you perceive the waves to be closer together than someone who's just floating there? Absolutely. Okay, you would perceive that the waves have a much shorter wavelength or a much greater frequency. Okay, if you're moving into them because they're moving towards you and you're moving towards them, you encounter them a lot more often than someone who's just sitting there floating. Okay, so all waves are going to have this Doppler shift idea, okay, or effect. Okay. That's more of the same here. Okay, so let's look at an example. Let's have you guys write this one down, and then we'll do it as an example. So, train's traveling at a speed of 30 meters per second. What did they just give me? Speed of the source, Vs. Okay, so 30.0 meters per second. Its whistle generates a sound wave with a frequency of 224 hertz. Which F is that? Right, okay, the one that we're not actually solving for. The formula solves for the shifted frequency. This is the original frequency. Okay, what is it on your formula stick? I never remember. Is that 0? Yeah, that's 0. Okay. So that's F0. Okay, 224 hertz. You're standing beside the tracks. Beside the tracks. Not on them. It's not good to stand on. It's better to stand beside them. Okay? And the train passes you with its whistle blowing. What's the change in frequency that you would detect? So basically we're looking for the Doppler frequency. I always put F1, but your formula sheet just says F. Okay, what would you detect for the pitch of the whistle if the speed of sound is 330 meters per second? So that's the speed of the waves. Okay, so F equals FO V over V. Am I adding or subtracting? As the train passes. Subtracting, coming toward me. It's worded terribly. I always say approaches or retreats, or coming towards or going away. I never say as it passes, because yeah, you might perceive as it passes to mean after it passes. I might perceive as it passes to mean it's coming towards me. As it passes actually does mean as it's coming towards you. Okay, after it passes would be, yeah, it's terribly worded. I don't claim, this is not my question. Okay, so in this case, minus the speed of the source because I have an approaching object. Okay? All right. So all I have to do is plug in my numbers on this one. So I'm going to have 224 hertz. Okay? I'm going to have 330 meters per second on the top. 330 minus 30. And then I got to multiply that by 224. Okay, that makes sense. It's a higher frequency. Okay, I should hear a higher frequency for an approaching object. It's quite a bit higher. Okay. What, 22 hertz? 22 hertz. That's a lot. You'd notice that for sure. You'd detect that. Okay, now let's look at manipulations of this formula, just so kind of see how that works. Okay, first manipulation. I want to solve for FO.
Divide by all V over V plus or minus Vs.
Yep. Take the whole bracket over to the other side, put it underneath. Okay, simplest thing to do. It's all got to be done first because it's in brackets anyway. Take it all over at once. That's actually the one I see people screw up the most, because they're trying to pick it apart piece by piece instead of just moving it all together. Okay, so if I was solving for FO, that's what I would do. Okay, what if I want to solve for the speed of the source? Subtract? Divide. Okay. All right, when I do that, that gets rid of that, and it gets rid of the need for these. Okay, now what? Vs is on the bottom, right? Okay. We're going to use one of the rules of algebra to our advantage. Yeah. I'm going to flip everything. Rules of algebra say as long as I do it to both sides, I can do whatever I want to an equation, as long as I do it to both sides. So my next step would be, I'm going to go FO over over just F. Okay? And then I'm going to have equals V plus or minus Vs over V. Now Vs is on the top where I can solve for it. What do I do with the V on the bottom? Multiply both sides by it. And then what do I do with the other V? Well, no, this V is always positive. So I'd subtract it. Now, for me, when I do this, I look, am I adding or subtracting? Because I do it a little bit differently. Let's say I'm subtracting Vs. I don't like to solve for negative numbers. So I actually add Vs over here. And then I subtract this whole thing over to this side. Perfectly valid to do that. I would do all the multiplication and division before I added or subtracted anyway. Okay? Then I'm solving for Vs and it's not negative. Because for me, I always forget that it's a negative number, and I put the wrong direction, all of that kind of stuff. But for this, it's not as important. If you get a negative number, don't make it negative. Okay? Just take the negative off of it. This is speed, not velocity. Okay? The plus or minus is already taken into account that it's moving towards or away. All right, so that's the little trick. The little trick is, remember, you can flip that, and that's how you would get Vs on the top. Those are the only two things you're going to be asked to solve for. Sorry, three things. F, FO, or Vs. We don't require you to solve for V because it's in two places in the equation. And we can't guarantee you've taken math yet, math 20 yet, so you may not know how to isolate something that's in two places at once. Okay, so you won't have to solve for the speed of the waves in this class. Okay. All right, everybody okay with how those questions work? Okay, give those two a try. Watch out for the one trick that's in here. Dirty trick. Okay, give number 4 a try here. We are looking for the speed of the train. In this case, that's the speed of the source. So on this one here, okay, we're told that the train is moving away. So right away, I always write like plus Vs on that, just so I remember. Okay, it's determined, the frequency of the whistle is determined to be 475 if the actual frequency is 500 hertz. So FO is 500 hertz. Okay, and F is 475. Now, the wording of that is not great. Okay, it's easy to get those two mixed up unless I think about this situation. The train is moving away. If it's moving away, the one I here should be lower. Okay, so if you're ever confused by the wording of a question, like that one says, the pitch is determined to be this much and the actual is this much, it's like, just think about the situation. Okay, think about the context of the question. It's moving away, so this one, F, the Doppler shifted one, should be smaller than the actual one. Right, so now we've got we know that the speed of sound in air, speed of the waves is 350 meters per second. All right, so F equals FO times V over V plus Vs. All right, so I'm going to divide both sides by FO. I'm going to flip both sides. I'm going to multiply both sides by V. And then I'm going to subtract V. So I'm going to have FOV over F minus V equals Vs. Okay, when I plug in my numbers, that's going to be 500 times the speed, which was 350, divided by 475 minus 350. Yep. Okay.
I just can't get the right answer. I don't know if I'm doing wrong.
For which one?
For both.
For both of them? Okay, well, let's have a look at number 1. Okay, so crossing the sidewalk, an approaching driver blows his horn. The true frequency, that's F0, is 264 hertz. Okay, the car is approaching at 60 kilometers per hour. That's the speed of my source, but I have to divide that by 3.6 in order to get my meters per second. Okay, and we are looking for the Doppler frequency, assuming the speed of sound is 340 meters per second. So for this one, we just have to plug in our numbers. And because it's approaching, it's minus. Okay, so we're going to have 264 times 340 divided by 340 minus 16.7. This needs to be done first. Okay, otherwise your calculator will do order of operations and you won't get the same answer. So 264 times, in brackets, 340 divided by, in brackets, 340 minus that number, in bracket, in brackets. Okay, should give us 278. Right. And we go over number 2 as well. Yep. All right. So for number 2, okay, the speed is 360 kilometers per hour. That means it's 100 meters per second. Okay, just divide by 3.6. So that we can do in our head. Okay. If you measure the pitch of its approaching engines to be 512, so that's the one we hear. That's F. Okay. What must be the actual frequency of sound if the speed of sound is 345? Okay, so F equals FO, V over, and it's approaching, so V minus VS. Okay, I'm solving for VO, so I'm just going to divide the whole bracket over. V over V minus VS. Okay, so when we plug in our numbers here, okay, we're going to have 512 divided by 345 over 345 minus 100. Okay, so 512 divided by 345 divided by 345 minus 100. I should have just put in 245. That was silly. Okay, so 364. Yeah, it's probably the brackets. Yeah. Okay, any other questions on those? All right, so what's another monkey wrench I could throw into a question like this?
Not give us the speed of sound, but provide the temperature.
Exactly. What do you think I'm going to do on the test? Yeah. Okay, so there could be the additional step of V equals 332 plus 0.6 times the temperature. Okay, it's just a second little step that I would throw into a question like that, because otherwise it's just one formula and it's too easy for you guys to throw something a little extra in there. That would be what I would do if it were me, and it is me. So, okay, see if we can solve this one. We're looking for how fast the car is traveling, and this is approaching, because it's worded poorly. Approaches. Okay, so 550 hertz is the original frequency of the horn. She hears 520 hertz. Wait a minute, that's not right. As he passes, this must be going away. How do I know it's going away?
Because the frequency is
Yeah,
lower.
the frequency she hears is different, it's lower. Okay, so this can't be approaching. Sorry guys, I didn't read that carefully. It says passes. See why you don't use passes in a question? I assume it means approaching, because I didn't read the rest of the question. Okay, so in this case we have a retreating source. Okay, so F is 520, and the speed of sound is 340 meters per second. So we're going to have F equals FO V plus Vs, because it's a retreating source. Okay, so we're going to divide both sides by F and then flip it. Okay, multiply both sides by V, that always happens, then subtract V from that side. So what we're going to have is 550 times 340 divided by 520 minus 340. That'll give us the speed of the car. So 550 times 340 divided by 520 minus 340. So it's moving at 19.6. We have 3 sig digs there. 19.6 meters per second away from the person.
And can I just see how you manipulated the thing?
Yep. Okay. Oh, sorry. This last step was I subtracted this V over to this side, so that's what this is. Okay. So, sorry. The final manipulation is this: FOV over F minus V equals Vs. Okay. Everybody all right with that one? Let's have you try this one. This one is a approaching one, and the person is standing on the tracks, which is not a good idea. All right, give that one a try, and we'll call it a day after that one.